So today we will do in the column of numbers 57 through number 70. So let's go ahead and jump in and take a look. Let's start out with question 57. Okay. We are going to be solving for x in this logarithmic expression. Let's see. There we go. So solve for x in this. So I have log base 2 of x plus log base 2 of 7 is equal to 3. Okay? So I need to somehow pull the x out of the logarithmic expression, which means I can do one of two things. I can either attempt to isolate this logarithmic term, and by moving this over to the other side, which is a valid solution, but when I rewrite this, I'll have a log in a power. So the more common way that I would generally represent this would be, hey, I notice I have a common log, they're both log base 2, and I have an addition sign, which means I can combine these into a single logarithmic term. So this will now be log base 2 of x times 7 is equal to 3, or an easier way to look at that is log base 2 of 7x is equal to 3. Now, with this expression, I can rewrite this in exponential form. And when I rewrite it in exponential form, I'm going to drop the base and swap. Not e, that's supposed to be a 2. Okay, so I have 2, I dropped the base, and I swap. So 3 is equal to 7x. Now, this is much more friendly to solve. 2 to the third power we know is going to be 8 is 7x. And to solve for x, I'm just going to divide both sides by 7. So I have 8 sevenths is equal to x. And there we go. It's the end of number 57. Let's take a look at number 58. Okay. Number 58 is a similar style question. We're looking at the log of 3 of 243 minus the log of 3 of 27 is equal to x. Okay. So with these values right here, we could work out each individual aspect and see what we'd get. Because I know that the log base 3 of 27, I'm saying 3 to what power is 27? So I know that this whole expression right here is going to be equivalent to 3. The third power of 3, because we have 3 times 3 is 9, times 3 is 27. So I know that's equal to 3. If I were to try and figure out what the evaluation of this is right here, well, 243. Not exactly familiar with my 3 tables as well as I should have. I'm going to say, okay, 3 times 3, this is 3 squared, cubed, fourth, fifth. I know this is the equivalent of 5. So all this question is asking me is, what is 5 minus 3? In which case is 2. So method number 1 says x equals 2. The other method that you might employ is, you notice that I have the same bases. So I could rework this as the same logarithmic expression. The minus sign means that this is the numerator, this is the denominator. So let's say method 2 is log base 3 of 243 as numerator, 27 as the denominator is equal to x. And it's a similar setup. 3 to what power is this? So 243 minus, or divided by 27 is going to give me 9. So what this is saying is that log of 3 of 9 is equal to x. So 3 to what power is 9? Well, that would be 3 squared. So I know that this is equivalent to 2. So we see that no matter how we do this, we get the same answer. Here I evaluated each individual log term, here I combined them and then evaluated them, but I get to the same thing. So that's number 58. Let's take a quick look at 59. Okay, so same style setup. I'm solving for x equals the log base 2 of 32 minus the log base 2 of 4. So I can work this just like I did before. I can evaluate each individual term, or I can combine them into one. If I evaluated each individual term, I know 2 to what power is 32? Let's see. We have 2 to And then we have 4, 8, 16, 32. So this is going to be the equivalent of 5. If I say log base 2 of 4, 2 to what power is 4? Well, that is going to be 2 squared. So what is 5 minus 2? Well, in this case, x is equal to a very poorly written number 3. If I wanted to evaluate this out into one logarithmic expression first, they have the same base and a minus sign. So this could be equivalent to x equals log base 2 of numerator and denominator. 32 divided by 4 is going to give us an 8. So this is really saying x is log base 2 of 8. 2 to what power is 8? 3. So no matter how we work it, we get the same thing. That's the end of 59. Let's take a look at 60. Okay. So we have 2 log expressions equals a third log expression. Let's go ahead and write this down. Log base 6 of 4 plus log base 6 of x is log base 6 of 2x plus 10. Okay. So now one of the things that you will notice is that when I have common logs, what I would like to do is I'd like to combine a log on both sides. And these aren't common logs. These are, let's call like logs. So log base 6, log base 6, log base 6. I want to combine them into a singular log on the left and a singular log on the right, in which case, if they have the same base, I can drop the logarithmic expression entirely. So let's take a look. If I can combine these are both log base 6 with an addition sign. That means I can take log base 6 of the product of these two terms. So 4 times x, log base 6 of 2x plus 10. Now that I have a singular log term, or what we call like logs, I could technically raise 6 to the power of both of these, which would cancel it out. Or an easier way to think of it is, if I have the same log on both sides and nothing else, I can just get rid of the log terms and say, what is 4x equals 2x plus 10? Forgot my 1 right there. Awesome. And in this case, it's just an algebra problem. Subtract the 2x, divide by 2. Awesome. Now, one of the things you will want to do every time you have a log is you do want to go back and check your work and make sure you don't do anything funny with the individual terms. So I'm going to go back and check. Remember, logarithms cannot be negative. So if I look at this, that works good. Log base 6 of 5, that works good. 2 times 5 is 10. 10 plus 10 is 20. This is all good, so that is a valid solution. We want to make sure that when we plug it in, let's say this was a negative 2, that would be log of 0. 6 to no power would give me a 0, so I know that even though it looks like that would be an answer, it wouldn't work. But we don't need to worry about that here. Everything worked out fine. So that was number 60. Let's take a look at number 61. Okay. So number 61, I'm doing the same thing right here. Log base 3 of 5x plus 8 equals log base 3 of 9 plus log base 3 of x. Okay. So again, I noticed that they're all log base 3, so they're like logs. What I want to do is combine these into a singular log term. Okay. So because they're both log 3 with an addition sign, what I know is I'm going to take the product of these two arguments. So log base 3 of 9 times x. And now that I'm looking at an equation with log base 3 on both sides, I know that those logs can basically be ignored. And I'm really looking at a question of 5x plus 8 is equal to 9x. In which case, in 2 steps, subtract the 5x and divide by 4, I get my answer. And again, with logs, we always want to go back and double check, make sure our answers make sense. Are they all positive? 5 times 2 is 10, plus 8 is 18. That's good. No issue here. Log base 3 of 2, that's a positive number. That's good. Awesome. So that is a valid answer. That's 61. Let's take a quick look at 62. Okay. Simplify the expression using properties of logs. I have the natural log of e to the 10th power. Okay. So we want to simplify this as best as possible. Well, let's go ahead, and I know that the natural log of e raised to the 10th power, the first thing I can do is relocate that power of 10 as a coefficient, which means this is really saying 10 times the natural log of e. The second thing I know is that the natural log is really just this. It's log base e. So if that's log base e of e, this is asking us e to what power is e? Well, e to the first power is e, so that's really just a fancy way of saying 1. So we're saying 10 times 1 is what? 10. Oh. So that was 62. Let's take a look at 63. We're going to simplify this expression using properties of logs. We're going to do the same thing again here. Natural log of e to the 7x plus 8. Okay, so the first thing that we want to do is we want to take the power and rewrite it as a coefficient. Now you want to be careful here because at 7x plus 8, you don't want to say 7x plus 8 times the natural log of e, because that would assume that only the 8 is multiplied by that e. What we want to do is we want to make sure that that 7x plus 8, it was a power. The whole thing is in parentheses, times the natural log of e. Now, it really won't affect this particular question too much, but it may affect it if this doesn't evaluate out to what we're about to see here. We know the natural log, again, is just a fancy way of saying log base e of e. And just like the previous one, e to what power is e? We know it's 1. So this is saying 7x plus 8 times 1. So I'm going to get my original power of 7x plus 8. Now, if that evaluated out to 2, let's say this was an e squared or some other value like log base 10 of 100, we would want to include those parentheses because that 2 would distribute to both those terms. As it stands, the 1 distributed doesn't really matter, so we got away with it, but just keep that in mind in the future. That was 63. Let's take a look at 64. Okay. So Connor's coin collection, which was worth $400 8 years ago, has been increasing in value by 12% per year since then. Use the formula A equals P times 1 plus R, all raised to the tenth power, to write an expression and find the current value of the collection. What's my expression? What's my value of the collection? Okay, so let's go through a couple of the things. We know this formula, A equals P1 plus R raised to the tenth power, is a way of saying I have compounding interest. So I know A is the original or the final amount. I know P is the principal. I believe this one is LE. R is the rate, and T is the time. Awesome. So if I have $400 8 years ago, okay, that tells me that my initial amount was $400. It also tells me it's been 8 years because we're looking for the current value of the collection. Okay, so the amount of time passing, we have 12% per year. So I'm looking at a rate of 0.12 per year. So I want to make sure my time, falling off the camera there, is also in years. So if that's 12% per year, how many years has it been? 8 years. That will give me my amount. So let's go ahead and figure this out. Okay. So if I plug all these values in, I get A equals 400 times 1 plus 0.12 raised to the 8th. This is answer number 1. This is your expression. And then the actual amount, I need to evaluate this out. Well, this is going to be 400 times 1.12 raised to the 8th. A couple different ways we can evaluate this out. We could plug it in all at once. which would be, let's figure out what this is. We have 400 times 1.12 raised to the 8th power. We'll get $990. And in this case, it's going to be 38 cents. I know that 5 should round up, but again, anytime we're dealing with money, we always round down. It hasn't quite appreciated up to the next penny. It's working there, but that penny hasn't come to us yet, so we can't assume that it will. So that is if I can plug this in all at once. If you don't have a calculator like that, let's take a look at how I would plug that in. Okay. So if I have one of these calculators, which are the most common versions, okay, what I'm going to do is I'm going to raise 1.12 raised to the 8th power. So 1.12 raised to the power of 8 equals that, and I'm going to multiply that times my initial value of 400. I'll get my $990.38. Awesome. So that's number 64. Let's take a quick look at number 65. Okay. So number 65 says, if $600 is deposited into a savings account which pays 4.8% interest, compounded continuously. So different than what we had up here where it's compounding per year. This is compounded every moment. How long will it take for the money to double? Round to the nearest 10th of a year. Okay, let's take a look. If I have this formula, A equals P times E to the RT. A we know is the final amount. P is the principal. R is going to be the rate, and T is the time. We know that E does look like a variable. We know E is actually Euler's number, which is equivalent to 2.71. We know that's a value just like pi, so I don't actually need to plug in a value for E. E is already in existence. So I want to see how long will it take for the money to double. Okay. Let's see. If my initial amount is $600, I know I want to find the amount for it to double, which means it's going to end up being $1,200. We have a 4.8% interest, so 0.048. And there we go. Let's figure out what we got going on here. Okay. So I've got everything but the T for time. Let's fill this out. So if this is 1,200, is 600 times E raised to the 0.048 T. I want to solve for T. Now this expression is going to be solved using a log rewrite. I don't know what power that is, so I'm going to rewrite this as a log, which means I need to isolate this base. The first step is to get rid of the 600, so I'm going to divide both sides by 600. I'll get a 2. And now that I have my base isolated, I can rewrite this in log, which means I drop the base, log base E, and swap. Drop the base, swap, equals 0.048 T. I know another way of writing log base E is just saying the natural log of 2 is 0.048 T. And to isolate my T, I'm going to divide both sides by 0.048. So the natural log of 2 divided by 0.048 is equal to T. And then in this case, if I evaluate that out, a couple ways I could do this. I could just plug it all in all at once if I have the ability to do that. So let's see, I have the natural log of 2 divided by 0.048, and I know I'll get an equivalent of 14.4405 years. We're rounding to the nearest 10th of a year, so we are rounding. So 14.4 years. If I don't have a calculator like this where I can plug it in all at once, we're going to have to do this in a little bit of a long form. Okay. So I'm going to take my 2. My natural log of 2 is that number. I am dividing this by 0.048, and I'll get my 14.44 years. Awesome. Takes a long time for that money to double. better invest now. Okay, that was 65. Let's take a quick look at 66. Okay, if $350 is deposited into a savings account which pays 5.2% interest compounded continuously, how long will it take for the money to triple? So exact same setup, I've just got a different set of numbers here. So let's go ahead and write this out. I know A equals P-E-R-T. A is my amount, my final amount. P is my principal or my original amount, principal. My R is my rate, and T is my time. I know E, as we discussed previously, isn't actually a variable. It's a number, 2.71828. It keeps going. It's just like pi. Okay. So my initial amount, I deposit $350. I want to see how long it takes for the money to triple. So I'm going to triple this. Let's see. That'd be 900 plus 150. I'm looking at $1,050. I want 3 times that amount. My rate is 5.2%, so 0.052, compounded continuously. I want to round to the nearest tenth, so I'm looking for time here. So just a little bit. Okay. So if I fill this out, 1050 equals 350 times E raised to the 0.052 t. Okay. I want to rewrite this in a log form, so I'm going to isolate my base, which means get rid of the 350. I know when I divide that by 350, I'll get a value of 3 because we're looking at tripling it. Cool. And now I can rewrite this. I'm going to drop the base and swap. So I keep the same base, but I'm saying the argument is now of 3. I know another way of writing log base E is saying the natural log of 3, 0.052t. I can get rid of that 0.052 by dividing it. So I have the natural log of 3 divided by 0.052 is equal to t. Again, if I have a calculator like this, I'm going to kind of work from the inside out. So I'm going to say, let's get this all in one shot. I have 3 natural log, this is my numerator, and I am dividing this by 0.052. And I'll get 21 point, we said, tenth of a year. So with this, I'm going to keep that as a 1. So 21.1 years. If I wanted to plug that into a different type of calculator, I can take this and say, okay, the natural log of 3 divided by 0.052, 21.1 years. Awesome. So tripling your money takes a long time. Again, better invest now. So now that we've seen that, we're looking at number 67, and 67 is going to be, we're looking at coterminal angles. So I want a coterminal angle that is greater than and one that is less than the given angle. So for 67, I have an original angle of 37 degrees. Let's take a look at that. So if we remember, coterminal angles mean I'm looking at this on, let's call this on the unit circle. So I'm looking at an original angle measure of 37 degrees. So that's 37 degrees. If I want a coterminal angle, what I'm looking for is I want another angle that ends in that same position. Well, good for us. If I want to go in the positive direction, this is going positive, which means counterclockwise. I'm going to keep going until I hit that same spot again, which means there's one angle. That's in the positive direction. So I'm going to take, okay, that's 37 degrees plus a full circle is 360. So 37 plus 360 is going to give me my positive coterminal angle. So 37, 360, this is 397. There's one that is greater than. One that is less than, well, I do that exact same thing. Actually, let's rewrite this right here, because I think that'll get a little confusing if I draw it on top. Okay. So we have our original angle of 37 degrees. Now, instead of going counterclockwise, or, as I wanted to say earlier, anti-clockwise, in the positive direction, I'm going to go clockwise. I'm going to go in the other direction. Oop. Actually, I don't start right here. I start on the x-axis. So I start right there. Ignore that. That doesn't exist. Okay. So if I start right here, I normally went positive, but in this case I went negative, and you'll see that I didn't go a full circle. I went a little less. So we know that a full circle would be 360 degrees, but I'm not going this little piece right here that was my original, so I'm subtracting 37 degrees. So let's see, that would be 330, 323 degrees. Pause. Negative. So I'm going in the negative direction, and I am adding. So I'm going in the negative direction. So I would have gone negative 360, but I'm saving myself from that 37. So I got that a little backwards in there, but we got the idea. So my one that is greater than is 397 degrees. My one that is less than is negative 323 degrees. Awesome. So we're going to do that a couple times. That was 67. Let's take a look at 68. So 68 is going to be negative 229. Okay, so we're going to do this the exact same setup. So negative 229 degrees. Okay, so we know the positive direction is anti-clockwise. If I'm going negative 229 degrees, let's see, that's 90, 180, 270. I'm somewhere in here. So right there, there's my 229 degrees in the negative direction. If I want to have a coterminal angle that is greater than, well, I'm going to start here and just say bloop. That's all I need to do. Okay? So if I were to continue going in this full direction, I would be going a full 360 degrees. However, I'm not going, so I'm going to take away the length of what my original angle was. So 229. So 360 minus 229, let's see, that's going to be 160, 140, 131. Boom. So I get 131 degrees, which is a coterminal that is greater. If I want a coterminal that is less than, well, let's take a look at it again. And this time I'm going to draw it appropriately. We know my original angle is right here. So if I need another value that's less than, I need to start at the same point, and I need to continue going in the clockwise direction, which means I can't be equivalent to it, but what I can do is I can pass it and keep going. Boom. So once I hit it, I've gone a total of negative 220 degrees, and I've had to add an entire circle. So I have a full negative 360, including the original 229. So let's see what this will give me. That is negative 589 degrees. So I have a coterminal that's greater and a coterminal that's less. That was 68. Let's take a look at number 69. Number 69 is 400 degrees. Okay, so what I'm going to do is I'm going to break this down into, okay, so 400 degrees. I know my original angle does one full circle, and then it continues a little bit more. So it looks just like that. So it goes one full time around and a little bit extra. So if I want a coterminal angle that goes in that is greater than, I'm going to say, okay, I need one that is higher. What you might be tempted to do is you might be tempted just to say, hey, let's do that. But we notice that that is actually going to be a smaller value. We could use that over here. So I would have that. I'm going to have to do the full loop. There we go. So I've got my 400 degrees. But now I'm equal to, so I'm going to have to do one more loop. Boom. Okay. So what I see here is I see two full circles. So I see 360 plus 360. I see my two full circles plus that original gap. So how far above 360 degrees was my original angle? Well, that little itty bitty bit right there is going to be 40 degrees. So that right there is 40 degrees. So I have one circle, two circle, plus the tidbit of 40. So 400 plus 360 is 760 degrees. There's one that's greater. Now, what I could do is I could say, well, let's do one that's less than, and swing my way all the way around, but I don't need to. If you wanted to see where it ended up, let's see, right here. Why don't I just stick with that original one? That's less than. My original one is less than, so that is 40 degrees. However, if you want to stick to the other one, there are multiple answers to these problems. So I could say, let's start here, go in the negative direction until I end up right here. Well, I know that original bit is 40 degrees, so I would get, okay, what would have been a full negative 360, I stopped just short by 40 degrees, which is negative 320. This is also a valid answer because it is also less than. The question doesn't say the first angle that is less than or the first angle that is greater than. It simply says one that is greater and one that is less. Awesome. So that was question number 69. Let's take a look at the last one in this column, question number 70. Okay. So question number 70 is negative 165. Perfect. So negative 165, if I look on the unit circle where that lands me, I know the negative direction is going to be 90. It's going to be somewhere in right here. And I need a value that is greater than. So what I'm going to do is I'm going to end up going in the positive direction. Boom. This is going to be greater than what would have been a full circle. So what would have been 360 degrees total, I'm falling short by 165 degrees. Okay. So that's going to be, let's see, 260, 200, 195. There we go. My first coterminal angle, which is greater than that, is going to be 195 degrees. For my second one, let's see. I need a value that's less than, which means I'm going to need to head in the anti-clockwise direction. So I'm going to start here, and I'm going to go here. Ooh. Not quite. I'm going to have to do one full circle again. And now we're good. So I've gone the original 165 and an additional 360 degrees in the negative direction. So negative 165 and negative 360. What's 460? 525. Boom. And again, as we discussed previously, I could keep going and keep going and keep going, and I'd have a bigger and bigger and bigger number in the negative direction. But in this case, we don't need to. And there we go.